probably I say some words to myself and where I come from. RWE, the company I work for, is one of the big four utilities in Germany, like Endesa in Spain. And myself, I've been working for 15 years now at the Research and Development Department at RWE. At RWE Power. RWE Power is the section of the power plant operators at RWE. And I'm working since 7 years on the development of a new storage technology on compressed air energy storage. And that will be one part of my presentation today. You asked me to make a presentation on this title, Energy Storage, the Future of Renewables. I put a question mark at the end because there are still some concerns and doubts, and probably we can discuss that later on, and you will see what I mean with that. So at the beginning, I would like to give you some information on what the situation in Germany is, what the German so-called Energiewende. A lot of people have tried to translate this word. Paradigm change is maybe a good one. So after Fukushima, Germany decided to get out of nuclear and get even stronger in the promotion of the renewables. That's what we call the Energiewende. And I would like to give you some information on what the German governments would like to deploy in Germany. So this is mainly the roadmap, let's say, for the German government, how to get to a more renewable future of the electricity generation in Germany. These are the goals in order to reach our goals in terms of CO2 reduction and deployment of renewables. The first thing I said is we want to phase out nuclear energy. Pierre Bernard yesterday said that is not a homogeneous opinion in Europe. Germany is one of the countries that definitely do not want to continue in renewables. And my company itself is affected by that. We have also nuclear. And but this is obviously the opinion of the society, and that's a good decision then, I think. Furthermore, we want to deploy renewables, yes, but in order to meet our tasks here in 2015, which is a quite long perspective, the German energy concept also includes a reduction in power consumption by 25%. Mainly by efficiency gains in the end customer sector. And it also requires 20% of import from neighboring countries. And this is necessary to fulfill the goals to reduce our CO2 footprint in Germany. But I have some kind of doubts if that really works out, because our neighboring countries would need to deliver this import as an export from their point of view, of course. And when do we need this? We need this mostly when renewables here are probably not available, if there's no sun and if there's no wind. And exactly in those times, they will have also not these power available. But however, that's the task. And I think there are still some challenges to go. So the following slides shows you what happened in the last years and what is the perspective, the outlook. You see the installed capacity in Germany of wind power in blue bars and photovoltaic in yellow bars. And that's what we heard today already 2 times. We experienced a huge peak in photovoltaic deployment in the last years in Germany, especially the years 2010, 11 and 12. We installed every year 7.5 gigawatts. That's a huge amount of photovoltaic. And this, of course, causes problems, especially in the grid and also for the power plant operators. And this has also a huge market impact. Why did that happen? Because I just saw that in Spain the largest deployment of photovoltaic happened in 2008, and after that, not anymore. So obviously something has been different in Germany, And the difference is the feed-in tariff that you get if you install a PV on your roof is getting down, is lowered every year. And in that year, you have the first installation. You are you have a guarantee to get for 20 years a certain value per kilowatt hour, and that is lowered every year. So what happened is that the panel prices ramped down quicker than the subsidies, and that's the reason why in these years these large amounts of photovoltaic were installed. So it's mainly subsidy driven. So the second question is, that was the slide before was the installed power here, but what amount of energy does this deliver? This is displayed here, and you can see, especially here on biomass production and also on PV, we experienced a real acceleration in the last years. And we in Germany have at the moment, this is 2013 values, at the moment we have more than 25% of renewable energy in the grid, electricity, I have to say, electricity in the grid, compared to earlier times before this peak we always had 5% of hydropower since decades. So the additional renewable energy we have in the grid is about 20% at the moment. And the problems that are related to that can be seen on the right-hand side. As you know, photovoltaic is only producing electricity if the sun is there, which is in the center of sunshine, Germany, probably not always the case. And wind also is very depending on the weather situation. This is a slide that I like to take because you can explain a little bit the problems we have to deal with. This is old data, but it doesn't matter. I can show you later on that this is also the case today. Mainly, what you see here is the power generation of wind energy converters in the year 2009. In 2009, we had 25 gigawatts installed. And there are 5 days in February where we had an initially strong wind situation, but followed by several days of nearly no wind, a so-called inversion weather situation where we had a really cold weather, and also all Germany was affected, and we had also a very large need for heating, for residential heating, and so forth. Also a large natural gas consumption during these days. So we have to cope with this high absolute power, but the second problem is these large energy gradients that we need to deal with in the grid. Also, on the one hand, the grid operator, but also the power plant operators. And then the third issue is we have long periods of calm weather where nearly no wind is produced, or wind energy is produced. So if we're now talking about storage, the initial idea is, hey, come on, let's take a storage, put the energy into it when it is not needed and it is produced by renewable energies, and take it out if probably the renewable energy is not available. But I just displayed here what the actual storage capacity in Germany is. We have about 7 gigawatts of pumped hydro storage in Germany, and it lasts for about 6 hours, then they are all empty. And if you now think about even out such a curve to a base load, you can imagine how many storage that you would need. And my guess is that in combination with wind, storage, although the function that storage can provide is mainly to even out this ramp here, because this ramp is getting even steeper when we are thinking about having not 25, but maybe 50 gigawatts in a few years. These ramps are critical for us. And if we're talking about storage that is connected to the transmission grid, like pump hydro, I think this will be the balancing of the electricity will be the issue. This is an example 2 years later. You see the same situation. So I just want to display this is not a single case. And since we experienced that, we analyzed the wind data of 20 years and we searched for periods where we had 10 to 12 days of calm wind situations or even longer. And you see here in these slides every year, nearly every year, we have 1, 2, or even 3 or more situations of these long calm wind situations where we have nearly no wind generation. So, as we know, we always have to keep generation and demand levelized at any second, and electricity is hardly storable. We have several different measures to realize this, and the first, and from my perspective, it will also be in the future, flexible power generation. We need flexible power plant, backup plants in order to deliver electricity when no wind is present, for example. The second is extension of grid measures, or grid extension measures. We in Germany and in large other areas in Europe as well, we need grids to transport, for example, from offshore wind farms the energy on land and also within the country to different regions. The third, maybe the third measure you can do in order to levelize these, to balance out demand and supply, will be smart technologies on the demand side. And of course, energy storage is one measure, but none of these measures are or have the capabilities to serve all the problems that we face in the future. I would like now to come to the topic of energy storage and to get a little bit deeper in the different technologies. Our focus was, of course, our focus was on the big, large storage technologies, and afterwards go a little bit more into detail in the ADELE project, the project I was coordinating for the last 7 years. So different storage technologies have different capabilities concerning energy capacity and power they can provide. And this graph here characterizes the different storage technologies for the applications. For example, what you see here is the energy capacity, and this is the power they can provide. And remind, this is a logarithmic figure. So we have the potable batteries, which have really few storage capacity, which we also have in our smartphones and so forth. And since we are talking about the integration of really gigawatts of renewables, and this may be for a longer time, many hours, probably days, maybe months, we are talking about storage, which is in the upper right corner. And what you find here is only pumped hydro and compressed air. Chemical storage is also probably an opportunity. If you talk about storing energy for more than, let's say, a week, you definitely have to go into chemical storage like electrolysis, hydrogen, and because otherwise the energy density is far too low and the impact would be too big. Only pumped hydro and CAS provide both at the moment, large capacity and power rating. So if we look at these two technologies, pumped hydro is at the moment the one that is has the highest deployment in the world. It provides excellent efficiencies of up to 70%, and is or from the technical properties are very, very good because of the fast reaction, fast response time. They can ramp up very, very quickly, and the problem is with this technology, especially in this dense populated Central Europe like Germany, or also in the countries around, it's very hard to find sites for new installations. Theoretically, the potential is huge, But you also have to have public acceptance if you build a large lake or large lakes, and there's always a big impact in the landscape affected by that. So it is problematic to build that. We just were incorporated in one hydro pump power plant project, and the time from idea to installation is more than 10 years. So compressed air energy storage has a far lower impact on the environment, on the landscape. Only the machine building, as you see it here, is visible. And the good thing is you can also build them in those areas where we expect these large wind energy installations in the coming years. But there are only two plants in the world that has been installed. One is in Germany, one is in USA. I will show later on how they work. The efficiencies of these storages is quite low. And compressed air energy is not a real storage alone. It's a hybrid of a gas turbine and a storage. You will later on see what I mean by that. So you need natural gas to operate that, and it has also a CO2 footprint by that. The technology I followed, or our company followed with a consortium, was this lower thing, this adiabatic CAS. I will later on explain how that works. That has efficiencies of up to 70%, so it's the first one big storage technology that is in the range of hydro pump storages. And it does not need any fuel and has no CO2 footprint, therefore. So how does compressed air energy storage work? So basically you draw electricity from the grid, you drive a motor, and the motor drives a compressor train. So the compressor takes ambient air, compresses it to a certain pressure, and the compressed air is then being led in a subsurface volume in the ground. During this compression, the air is heated up, and since you need to feed this air in a cold manner into the ground, you need to reject the heat to the ambient. So this heat is lost, and that's the main driver for the efficiency loss there. So when you discharge, you let the heat out of the air out of the caverns, feed it into the combustion chamber of a gas turbine, and then produce electricity again. The second plant in the US, being built in the 90s, has one enhancement. It makes use here of the flue gas temperature, and in an exhaust recuperator, the cold cavern air is heated up before it's being applied to the turbine. So that's the main difference here, and that affects efficiency boost up to 54%, which is good, but still far away from the 80% of an hydropump storage. So I'd like to explain you now what we tried to develop in the last 7 years. The process of the ADELE concept, which is an adiabatic concept, is quite similar but different in one important way. If you charge, you take also electricity from the grid. You drive a motor that drives a compressor. You draw ambient air, and the ambient air is compressed here and heated up. What we now do is we do not reject the heat to the ambient. We keep the heat in the air and apply this hot compressed air to a so-called thermal energy storage. It's a heat storage in order to keep that heat for later use during turbine operation when we want to discharge. So what does this heat storage look like? We designed it as a huge pressure vessel, and inside the pressure vessel is a solid material, and the hot air gets in direct contact to the solid material and transfers its heat to this material. It can either be ceramic bricks or spheres as a pebble bed, or it can also be natural stone. So in this case, the storage is cool, and when you now let the hot air flow through the storage, to the thermal energy storage, that heat front is pushed to the bottom. And if you do that long enough, the heat storage will be filled. And the cooled air is then being led via piping through a wellhead, where it is afterwards being stored in a subsurface cavern. If you now want to discharge, you just reverse the process. You release the air from the cavern, let it flow in the opposite direction through the thermal energy storage. The air is heated up, and the pressurized hot air is then being fed to a turbine where it's expanded and produces electricity. But there's no combustion needed anymore. There's no fuel needed. Just the hot pressurized air is expanded and produces electricity. So that's the main difference in this concept. So what did we do? We started 2008, first with a feasibility study jointly with General Electric in order to figure out whether they can provide such turbomachinery equipment. And after a successful feasibility study, we initiated a research and development program to address all the technical questions we have. Here's some data is given concerning the power and the capacity. We intended to have 260 megawatts of turbine operation power and a storage capacity of 4 hours, what leads then to roughly 1 gigawatt hour of storage capacity. We had the technology partners on board here that you need, which is ESK. It's a company of RWE that designs such caverns in the ground. General Electric, I just mentioned, concerning the turbomachinery. And the DLR, as well as DLR is the German Aerospace Center. They have very much knowledge concerning these heat storage materials. And at Züblin is a construction company which decided to build, or which designed this thermal energy storage. So what topics do you need to address when it's complete new technology? And a lot of questions arise, and were addressed during this R&D program. General Electric, first of all, had in their scope the modeling of the overall process and some optimization measures in order to also not to design steady state operation, but also ramping up and ramping down, because we want to have a fast reacting plant. On the compressor train and on the turbine, a lot of detail engineering had to be done, because this compressor train does not exist of one machine. There are several machines after another, either 2 or 3. First, an axial compressor, which is available, and then followed by 1 or 2 radial compressors. These radial compressors are normally not operated at these high temperatures, so there were many detailed design aspects being addressed. For example, if you heat up and cool down this machine, you have extension of the material and shrinking, and these clearances have to be carefully looked at. Also, the loop oil system mustn't exceed 80 degrees C. This is quite difficult if at the last stage here you have 600 or 650 degrees C. So there were a lot of detail engineering to be done in order to figure out whether these machines can be built up. Concerning the turbine, we did not want to develop completely new machines. We wanted to rely on existing machines, but concerning the turbine, there are 2 turbine types available: steam turbines and gas turbines. Gas turbines normally are very quickly operable. You can ramp them up and very quickly. Steam turbines, on the other side, can withstand these large pressures. Gas turbines operate normally at 15 bar, 20 bar. The newest Alstom GT26, for example, they operate probably at 35 bar, but not at 70 bar as we would like to do. So steam turbines, on the other hand, they operate at 200 and more bars. That's not the issue, but if you want to have machines at this pressure, you need thick wall thicknesses. in the housings in order to withstand the pressure. But this is counterproductive because these thick wall thicknesses, the material needs time to heat up, and in order not to provoke cracks, it needs to be slowly, smoothly heated up. So it's problematic, and we had to combine design principles from both, from turbine and gas turbine and steam turbine operations or concepts. So the technology we had to design at the thermal energy storage mainly categorized in three blocks. It's the pressure vessel itself that was designed by Züblin, but also Züblin designed not a metal-based pressure vessel, because if we normally you would do a pressure vessel also from metal, right? And since we need a huge volume, the wall thicknesses of these pressure vessel would be too big. It's not available on the market, this material, and it's not affordable either. So Züblin, as a construction company, designed a pressure vessel based on a concrete material, a pre-stressed concrete design, and this was what they did in the program. Furthermore, the insulation needs to be very high sophisticated, because the concrete mustn't see the temperature, because if the concrete gets above 80, 90 degrees, it loses its stability and does not carry anymore the pressure. So we needed a good insulation there. And last not least, of course, the inventory material. What we did is, with the inventory material and with the insulation, we took hundreds of different materials and samples and cycled them in ovens and analyzed them, whether there was a change in the material or not, and in order to figure out which is suitable or not. The DLR has, that's the picture on the bottom here, has a test rig where you can test such an assembly of inventory material and insulation and cycle it time-wise very often. So you can figure out whether the assembly or the design is good or not. Concerning the cavern technology, as I said, you need a volumetric storage in the ground, and our company partner ESK was the relevant one to investigate the open questions there. Cavern storage is a well-known technology in natural gas storage, and basically it works as follows. You need a geological salt formation, here indicated as blue, in the ground, a natural gas salt formation, and you dig a hole into the salt and pump fresh water into it. The water solutes the salt, and if you don't do that, and the saturated solution is then pumped up again, and if you do that long enough, you get these cavities here, which you can use for gas storage or for compressed air storage. These storages here are huge. They can be 300, 400 meters high. The Eiffel Tower fits in there. Imagine that. That's really huge cavities. So what ESK did is we needed to analyze material selection, because since we have oxygen present, water, humid air, and salt, this is a very corrosive atmosphere. With natural gas storages, this is not the case, because there's no oxygen present. So we had to carefully select the material. We did long-term testing there, accelerated lifetime testing with these materials that we selected. Thermodynamical process modeling was there, but also the diameter. Normally in natural gas storages, you do not have these diameters that we use, and the diameter is normally limited by the drilling equipment that is available on the market. So we had to look into that and figure out whether there are alternatives. And of course, last but not least, the site screening. We do not want to build such or develop such a technology just for one site. This technology should be applicable at many, many sites. And just to give you a flavor, here's a picture, a map where such salts, these salt structures are available in Europe, and they are in Germany very large. There's a very large depletion, or you find large areas where you can find this salt, but also in other countries, and what is probably interesting for you, also in Spain, and I think here in this area there are also natural gas storages in salt. Okay, we figured out that we would build this 260 megawatts not in one single train, but in 3 parallel trains. So what would follow now is a demonstration project, and we would of course only build one single single train for a demonstration plant. What we also figured out is that unfortunately the costs are very, very high, in the range of 2,500 euros per kilowatt. So we intended to bring the costs down. So I just talked about the ADELE project, the development project. What followed was the ADELE-ING project, what is the engineering for a first demonstration plant. That was the objective. And at the end, there should be a final investment decision possible. And as I just said, we figured out in the ADELE project that the costs were too high. During the ongoing of the program, we had a lot of ideas how to make it cheaper, but we didn't have the time and the money and the resources to go to investigate all of the different paths that we had there. And that's why we put one phase at the beginning, the conceptual review phase. And that's what I like to address now. We figured out that we wanted to, this is our initial installation as I just described, but we wanted to investigate if that system will be far cheaper when we bring the temperature down. The background is, if you go for 650 degree, you need nickel-based alloys, which is unaffordable. That's something that we just figured out, that the piping for such a plant cost the same as the rest of the plant. That was something very surprising for us. But these are the experience you make when you get from research to realization. And a second idea was to put this thermal energy storage in a secondary loop. Why did we want to do that? Because in a secondary loop, you would not need these high pressures anymore. You would transfer the heat here to in a heat exchanger to a secondary loop, and this secondary loop here can be operated at far lower pressures. That would make this pressure vessel far cheaper. The third concept would be a molten salt thermal oil concept. So the hot air is being fed to a heat exchanger. It transfers a certain amount of the heat to a molten salt system, let's say from 600 to 300 degree, and then from 300 to 50 degree to a thermal oil system. Well, the decision to go for such a regenerative storage that I explained at the beginning was made many years ago, and the development on the concentrating solar power plants, which use these molten salt and thermal oil, they had gained experience, and we wanted to check whether this is probably now, today, the way to go. And the fourth system is a so-called multi-stage system where we go a different way. The first compressor compresses the air maybe up to 15 bar and 300 degree. We take out the heat here in the first thermal energy storage. Then it's compressed, it's further compressed again to, let's say, 300 degree, and then we have a molten salt system that stores the heat in a second step. So multi-stage concept. And these were the things, the main driver was bring costs down. Here is a picture which may display you that bringing down the pressure for such a thermal energy storage is a good idea. On the left side here, on the upper left side, you see the cross-section of such a thermal pre-stressed concrete design at 65 bar and at 15 bar. And it's easily visible that it's far simpler, you need less material, you need less of these pre-stressing vanes and so forth. So that can be far more cheaply built. We also did not investigate that just in theory. We built such a cross-section, a slice of such a thermal energy or vessel here in a test environment, and wanted to figure out if this construction is really reliable. In this black line here, this is a towel. Let's say you can fill it with water and pressurize it, so you can cyclically pressurize this outer ring. This outer ring here is the one that is the pressure vessel, and with this construction on the inside and this black pillows here, we can pressurize this outer ring and make tests with that. Here you can see a picture during the construction of that. It's quite big and quite interesting, really. So, finally, what was the winner of our investigation? Well, the winner of the investigation was, and that was a surprise, 3 systems operated really similar, economically wise. That's one is the molten thermal oil system, and the other one is the multi-stage system, which also contains one of these thermal energy storage, as I just described you on the picture before. So we ended up more or less at temperatures, at prices of 1,300 euros per kilowatt hour installation costs, and efficiencies of 66 to 68%. That's what our estimation is at the moment. And that's the result of this first year of investigation. So this was the technical part of that. We as developer can do everything to bring costs down, to adapt technical properties, to make to realize fast ramping up and ramping down capabilities. But the other side is the revenue side. If you want to install and build something, we want to get the money for your investment back. And this situation has decreased, obviously, in the last years, very dramatically in Germany. And that's what I would like to address now. And what you, on the first view, you would not expect that photovoltaics would bring the cost for storage down, or would not the cost, but the revenues for storage down, but this is definitely the case, and let me explain why. In order to do so, we need to get a little bit into the market pricing mechanism. How does that work? What you see here is the so-called merit order. At any time, any hour of a day, the market players give bids into their market and offer their electricity. The demand here has a maximum, varies between a maximum and a minimum demand. In Germany, this is about 80 and 40 gigawatts in Germany. So, and this merit order is listed up, the power plants are listed up by their marginal costs, the cheapest first, and then the next, and the most expensive at the very last. And the costs are only the variable cost, the marginal cost. So the nuclear power plants have the lowest marginal costs. The lignite, it's mainly they are mainly listed up by in the order of the price of the fuel they need. Natural gas is the most expensive gas fuel, and therefore they are normally used as peak power plants. So what happens now? If you want to exceed the renewable energy sources here, if you want to have more of them, the renewable energy sources in Germany gain priority. The grid operators collect them and bring them on the market without any bid size, so at €0 more or less. So they are taken always, and only the residual load has to be provided then by the conventional power plants, which are listed up in the merit order. And so what happens now if you exceed that is that the natural gas power plants are falling out of the market and are not operated anymore because they are not taken anymore in the market. So this is what we at the moment really experience, and this is why not only the price is falling, but also the price spread between peak demand and off-peak demand is shrinking. And storage basically live from buying at low prices and selling at high prices, and the difference between that's what the revenues come from for storages. And this obviously has been lowered in the last years very much, especially due to photovoltaics. Why especially photovoltaics? That's because you can see it here. This is the demand curve here over several days. And photovoltaics obviously feed into the grid when the demand is highest, namely during the daytime. And since they gain priority, only the rest has to be fed by or being served by conventional power plants. And this has been evened out in the last years. So the level is nearly stable. And also the price, because the price directly corresponds with the demand, as we have seen before. So the pricing mechanism has led to the situation that for the storage economics have been getting worse in the last years. And here you see that the price spread is only a few euros per megawatt hour. In former times it has been 20, 30, 40 euros, the price spread between day and night. And that has been leveled out. Sometimes even the here it is the case, the peak price is even lower than the base price, so very strange, but that's reality. And this is just to display you that that this is for us as a power plant operator reality. This is the normal operation of a natural gas plant, a PICO, which operates a day during daytime. And you see here the usual operation in 2009. Every day it is operated, every night it's shut off, and during the weekends it's normally also shut off. And 2 years later, the dispatch of this power plant looked like that. And as a power plant operator, you can do that probably 1 or 2 years, and then you will close that plant because it doesn't earn any money anymore. And that's exactly what happens in Central Europe now. And we have been closing a brand new combined cycle power plant in the Netherlands with 3 GT26 gas turbines, 60% efficiency. We close it down because it's not operated. That's the case. And so far, this is also the problem at the moment for energy storage, which are operating on the markets. And we will see what happens in the future. And at the moment, we decided not to go the further step. We need to go into the investment. And with these circumstances, you cannot convince a board to spend 200 million euros into such a demonstration plant. But what you also have to keep in mind is if you develop such new technologies, you need, as you saw, 10, 12, 15 years to get the first plant online and gain experience. But the reality here is far quicker. With PV installation, you have in 3 years 25 gigawatts installed, no problem. Yeah. Okay, so I'd like to go to summarize what I said. So the renewables and also the combined heat and power generation, which is also on the task list in order to reduce our CO2 footprint, calls for grid extension measures, but they alone will not be sufficient. We need flexible power operation and maybe storage if the market design allows for that. But because you have always options, and the technologies that will win will only win if there is an environment where they can re-earn the investment, which is obviously at photovoltaics at the moment the case. And the adiabatic compressed air storage is, from our perspective, after hydropump, the first choice to take. Hydropump storages will stay the best and the most economic ones if you have the opportunity to build them. It's still not available. We need a demonstration before we could do that. before we could speak of market maturity. The cost reduction endeavors, we did our best. We really are now in the range of, with the investment cost of those of hydro-pumped storages. But there is no big further potential to further bring the costs down. So we need also the revenue side that needs to be enhanced in order to allow for storages to operate and to be built. Yeah, and finally, the regulator will decide how the market mechanisms will be, and this will then decide which technologies will the one who will survive and will emerge. Yeah, so I'm at the end of my presentation. I would be happy if we could discuss this a little bit more and open for questions.